Today we are going to discuss Kirchoff's rules or Kirchoff's laws. Kirchoff's rules or Kirchoff's laws, you will find it very handy in solving problems there of resistances where resistances are not directly connected in series or in parallel, or there are your complex network problems. But at the same time, let me tell you that it is not that Kirchoff's rules can be applied only to the complex problems or network. You can use it even for the simple circuits. Kirchoff's rules are two. One is called point rule and other is loop rule. So let's discuss these one by one. Point rule says algebraic sum of the current meeting at a point is zero. That means mathematically we can write this as summation I as 0. If you take a circuit where through different branches the current are either going towards the point or they are leaving there. So suppose it is like this. We have I1 going towards the point O, I2 leaving, I3 is going towards the point, I4 is going towards the point, and I5 is leaving from the point O. If you want to apply point rule here, we'll have to take one direction as positive. So suppose we take incoming current as positive. So in that case, I1 will be positive. So if I take incoming current positive, I1 is positive, I2 is negative because it is outgoing, I3 and I4 are positive, and again I5 will be 0. This we have taken where incoming current were taken positive. So this can also be written as your I1 plus I3 plus I4 equals to I2 plus I5. Now, what are the terms here on left side? These are sum of incoming current. I1, I3, I4 are the incoming current. And I2 and I5 are outgoing current. So this is your sum of incoming currents, and this is your sum of outgoing currents. So sum of incoming current is equal to sum of outgoing current. So point rule we can also state as sum of incoming currents is equal to sum of outgoing current. So this is basically point rule. Remember that point rule is a consequence of law of conservation of charge. This is a consequence of law of conservation of charge. Because if you assume that incoming current is less than outgoing current, if incoming current sum is less than outgoing current sum, it means from a particular point the charges are being created. That is why outgoing currents are becoming more, which will violate law of conservation of charge. Similarly, if the incoming current is more, outgoing currents are less, that will also indicate that some charges are getting destroyed at a particular point or they are vanishing from that point. That will also violate law of conservation of charge. That is why sum of incoming current at a particular point must be equal to sum of outgoing current. This is your point rule. Now let's take loop rule. Loop rule says algebraic sum of the potential difference across different arms of a closed loop is 0. Algebraic sum of the potential difference across different arms of a closed loop is 0. That means we are taking summation potential difference across a closed loop as 0. And in a circuit where you can get the potential difference, it may be the potential difference across a resistor, it may be potential difference across a source of EMF or cell or battery, whatever you are taking. So this can be written as summation IR, which will give you algebraic sum of the potential difference across the different resistors there, plus summation E equals to 0. This is your algebraic sum of the potential difference across the source of EMF, that is the battery or the cell. So this is 0. Now this is the mathematical expression of loop rule. Loop rule is based on law of conservation of energy. Point rule was based on law of conservation of charge, and loop rule is based on law of conservation of energy. Now, to apply this to a given closed circuit or loop, we have to follow some sign convention. So, we are using sign convention where we take rise in potential as positive. So, taking rise in potential positive. So our discussion will be taking rise in potential positive. So for first case, for potential difference across a resistor, while passing through a resistor in same direction of current, we take potential difference negative. If you are going in the direction of current, we take the potential difference as negative. Whereas in opposite direction, it will be positive. So suppose you have a resistor R, current is I. If we move from left to right, then we are going in the direction of current. So this is, we are going in the direction of current. So we'll take the potential difference negative. Whereas in opposite direction, we are going in opposite direction of current. We are moving from right to left. Then we are going in opposite direction of current. So here it will be taken positive. Now why we are taking this one? Suppose I take this as point A and this as point B. If we are moving from A to B, that means we are taking potential difference between point A and B. So obviously potential difference between point A and B will be potential of B minus potential of A. Okay, that is the potential of final point minus potential of initial point. If you are moving from left to right, or current is going from left to right, that means it is going from higher potential to lower potential. Obviously potential of A is more than that of B. So B is at lower potential than A. So this term will be negative, and that is why we take this one as negative. Whereas in opposite case, if we move from B to A is at higher potential. So obviously if you take VA minus VB, this will be greater than 0, and we take this one as positive. But here you just remember that if we go in the direction of current while passing through a resistor, then we take potential difference negative. In opposite direction, it is taken positive. So for potential difference across a source of EMF, it is suppose E. While passing through a source of EMF from negative to positive terminal, we take potential difference positive. When we pass from negative to positive terminal of a source of EMF or a cell, then we take potential difference positive. In opposite direction, it will be taken negative. So when we move from left to right, it will be positive. And when we go from positive to negative, it is negative. Okay. So this will be applying. Just to remember, you just consider For the cell when we are passing, the terminal through which will come out, it will be the sign of that terminal. It is just to remember. Like here, if you are going from left to right, we are coming out from the positive terminal. So we'll take this one as positive. When we are moving from positive to negative, we are coming out from negative terminal. So it is minus C. But of course, the statement is that when we are moving from left or negative to positive terminal of a battery or cell, then EMF will be, or potential difference will be taken as positive. When we move from positive to negative, it will be taken negative. But just to remember it, you can take that whatever terminal we are coming out, ultimately, it will be the sign of that terminal. Remember, when we apply Kirchoff's rules, we have taken here all these sign convention where we have taken rise in potential positive. You can take rise in potential negative also. Then whatever equations you will frame, you will get just opposite sign there. Solving numericals by any of these sign convention, you will ultimately get the same result. That means magnitude wise it will be the same. Sign will be opposite. But when you try to explain that or interpret it, you will get the same conclusion. But I will suggest you use a rise in potential positive for solving numericals, because this is how it is given in the NCERT book and other books also. So you will find it easier or to apply to the different problems there, and in the board examination also you will not have any problem there, because the marking scheme and other will be based on that only. Let's now apply Kirchoff's rules to Wheatstone bridge arrangement. Here, Wheatstone bridge will have resistances like P, Q, R, S and G connected in this fashion, and we want to find the current through different branches. For that we are applying Kirchoff's rules. So let's assume that it is connected to a source of EMF E. If it is connected to a source of EMF E, it will be drawing some current. Let the current drawn from the source be X plus Y. If this X plus Y current reaches point A, it has now two branches to flow. It is your AB and AD. So suppose in the branch AB, it is X current which is going, and through AD, it is Y. So you can see we have applied point rule here. Sum of the incoming current must be equal to sum of outgoing current. Here the current which is reaching here is X plus Y, and the current which is leaving is X and Y. So combined current is your X plus Y. When this X current reaches point B, again it has two paths to flow. We assume that through BD it is Z current which is going, and through BC it is X minus Z current, because whatever will be the remaining current, it will be going through that part. At point D, from BD, it is Z current is reaching here. Through this branch AD, it is Y current reaching there. So the current through the branch BC will become Y plus Z. So it is Y plus Z. At point C, X minus Z is coming from this side. Y plus Z is reaching here. So the total current will be X plus Y. It is X minus Z plus Y plus Z. So this is your X plus Y and current which is reaching at the other end of the source of EMF, or the other terminal of the source of EMF, you can say. Now, whether your current distribution in the given network is correct or not, for that the best test is you just see from a particular point, whatever current is leaving, is it the same current returning to that point or not? Say for example, we are taking that it is a cell through which current X plus Y is coming out from positive terminal. It is same x plus y is reaching here. That means our current distribution is correct. We have used three unknowns, x, y and z. X, y, z, if the three unknowns are there, to get their values, we need three equations. So we will apply loop rule here to get those three equations. And solving those three equations, we can get the value of unknowns. So let's apply loop rule to first loop. We take the loop, say A, B, D, A. So in loop A, B, D, A. From A to B, if we are going in the direction of current, because current X is also going from A to B. So for loop rule, we have used the sign convention, taking rise in potential positive, that while passing through a resistor in same direction of current, we take the potential difference negative. So with that, it will be minus Px, A to B. Potential difference between B and D, this will be minus Gz, because again we are going in the direction of current Z. But from D to A, when we are going in opposite direction of current. Current is, Y is coming from A to D. We are going from D to A. So this will be plus Ry. This is equals to 0. Summation IR is equals to 0. There is no cell here. So it will be only summation IR equals to 0 there. So this is our first equation. Let's take the second loop. In loop BC, DB. If you take the loop BC, DB, in that case, it will be how much? From B to C, we are going in the direction of current, so it is minus Q, X minus Z. C to D, when we are going in opposite direction of current. So it is your S, Y plus Z. And through D to B, we are again going in opposite direction. So it is Gz equals to 0. Or we can write minus Qx plus Sy plus Q plus S plus G. Z equals to 0. Let it be equation number 2. Now, we have to take the third equation also. If you have taken first loop as A, B, D, A, second loop as B, C, D, B, you cannot take A, B, C, D, A as third loop, because it will not give you any different equation. It will be just giving you the sum of the equation which you have got while taking the first loop A, B, D, A and B, C, D, B. So you cannot take this as the third loop. But be very clear. It's not that you cannot take this big loop A, B, C, D, A. You can take this as one loop. But then the second loop, which you can take for framing equation, may be either A, B, D, A or B, C, D, B. That you can take. But you cannot take all the three here simultaneously. So for that, what we are doing, we'll take now the third loop as A, B, C, E, F, A. Or you can take A, D, C, E, F, A. Any one closed loop you can take. So we are taking loop in loop A, B, C, E, F, A. So here A to B, when we are going in the direction of current, so it is minus Px. B to C, again we are going in the direction of current, so it is minus Q, X minus Z. And here there is no resistance. If internal resistance of the cell is there, then in that case you can take for the potential drop across that internal resistance of the cell. But here now it is the source of EMF only. And when we are moving from E to F, we are going from negative terminal to positive terminal of the cell. So this time we'll take the EMF as positive, because when we pass through the cell from negative to positive terminal, then we take the potential difference positive when we have taken rise in potential as positive. So this will be plus E equals to 0. So now you have a minus P plus Q X plus QZ plus E equals to 0. Let it be third equation. We have taken this minus Px minus Qx minus Z plus E equals to 0. So it is your minus P plus Q plus QZ plus E equals to 0 as third equation. Now you have three equations. Three unknowns were there, x, y, z. So solving these, you can get the value of unknowns. If there is any numerical where the value of the resistances will be given, you will have to basically solve that to get the value of unknown. So this is how you can apply Kirchoff's rules to the Wheatstone bridge arrangement and get the value of the unknowns there. Let's now try to get the balanced condition of Wheatstone bridge. In Wheatstone bridge balanced condition, no current flows through galvanometer arm. This BD we call it as the galvanometer arm because we connect a galvanometer here in this arm when we are using Wheatstone bridge as a practical circuit there. So in balanced state, no current will be flowing through this arm because potential difference across B and D will be 0. And why potential difference is 0? Because the potentials of B and D are equal. In balanced state, potentials becomes equal at point B and D. So potential difference will be 0 and hence no current will be flowing through galvanometer arm. In balanced state, Z will be 0. Current through galvanometer arm is 0. So Z is 0. So if I put this Z 0 in first and second equation, putting it in equation 1 and 2. So if I put in first equation, it is minus Px plus Ry equals to 0 or Px equals to Ry, and that gives P by R equals to Y by X. Let's call this as equation A. If I put it in second equation, then what will get? It will be minus Qx plus Sy equals to 0 or Qx equals to Sy or Q by S equals to Y by X. This as equation B. Now if I take equation A and equation B, so from equation A and B, what we get? P by R equals to Q by S or P by Q equals to R by S. This is the balanced condition of Wheatstone bridge. Whenever we get P by Q equals to R by S, we take it as the balanced condition of Wheatstone bridge.